If a function is one-to-one, it is invertible. If I have the graph of a function, I can create the graph of the inverse function by reflecting f across the line y equals x. But what if I don't have the graph? What if I just have the function rule? How do I find an inverse function in that case? To find the inverse function of f of x algebraically, we're going to use something called the switch and solve technique. So first of all, if our function is in function notation, we're going to put it back in the form of two-variable notation by replacing f of x with its equivalent y. Then we're going to switch x and y. Remember when we defined an inverse function, we saw that the domain and range switch. By switching x and y, we represent that in the function. Then, number 3, we're going to solve for y. By solving for y, we're identifying all of the correct operations that will belong to the inverse function and in the proper order. And then finally, number 4, we'll go back to function notation by replacing y this time with f inverse of x. Let's give this a try on example 8. Find the inverse function, f inverse of x, of the given function. So on example A, we have f of x equals the linear function x plus 3 over 4. So the first thing I'm going to do is take it out of function notation by replacing f of x with y. So we have y equals x plus 3 over 4. Then we're ready to do the switch and solve technique. So I'm going to make a note over here. Something new is happening. This line is not equivalent to the previous line. It's going to be a new function. The y becomes x and the x becomes y. So we have switched x and y. And then we want to solve for y. So to solve for y, the first thing I would do here is multiply both sides by 4 to cancel that denominator. This gives us 4x equals y plus 3. Then, of course, we could subtract 3 from both sides. 4x minus 3 equals y. And I'm going to flip it around so that we can have y on the left. Y equals 4x minus 3. And that is our inverse function. So we'll replace y with f inverse of x. And our inverse function is therefore the linear function 4x minus 3. Now at this point, if we wanted to verify that that was the inverse function, we could graph both f and f inverse on the same set of axes and visually observe if they're reflections of each other about the line y equals x. In the next video, we'll look at a more reliable algebraic way to verify those two inverses. Let's take a look at example B. We have the function f of x equals x cubed minus 2. So to find the inverse function, I'm going to start by replacing f of x with y. Then we're ready for our switch and solve technique. So we're going to switch x and y. This gives us x equals y cubed minus 2. And our goal now is to solve for y. So to solve for y, we need to add 2 to both sides. Notice adding 2 is the inverse of subtracting 2. I'm going to go ahead and switch my equation around here, call it y cubed equals x plus 2. To solve for y, we need to clear that exponent, so we can do this by taking the cube root of both sides. The cube root function is the inverse function of cubing something. So again, as we solve for y, we're identifying all of the appropriate inverse operations and in the correct order. So now we have our inverse function in equation form, and we want to rewrite it in function notation. So we could write f inverse of x equals the cube root of x plus 2. Now, if you think about transformations, it's pretty easy to mentally verify how f and f inverse are in fact inverse functions. In fact, let's just construct a quick sketch of these two graphs. Remember, to determine if a pair of functions are inverses, we look to see if they are reflections across the line y equals x. So let's graph the original function x cubed minus 2. Remember, the parent function for a cubic function is this little vertical squiggle shape. But because we have a minus 2 out here, that's going to shift our parent function down 2 units. So rough sketch, x cubed minus 2 looks something like this. If we look at our inverse function, we have the cube root of x plus 2. Remember, the parent function for a cube root function was that sideways squiggle function. But because we have a +2 here underneath that radical, we know that's going to shift that cube root function to the left by 2 units. So let's think about moving that left 2 units and constructing a quick sketch. Okay, so the green curve was our original cubic function. The blue curve was our cube root function. And notice they are mirror images of each other across that line y equals x. Once again, in the next video, we'll look for an algebraic way to verify if those two functions are inverses. Example C, we have the rational function f of x equals 2 over x minus 3, and we want to find the inverse function. So let's replace f of x with y to begin with. And then we're going to switch x and y to get x equals 2 over y minus 3. And then our next goal is to solve for y. The problem here is that y is in a denominator, so we're going to get it out of the denominator by multiplying both sides by that denominator, y minus 3. And I'm going to switch the order of these factors here on the left side and call that x times y minus 3 equals 2. So don't forget, our eyes here are on the y. So to get y by itself, you've got a couple of choices here. You could go ahead and divide both sides by x. But for instructive purposes, I'm going to take a little bit of a different route here, and I'm going to go ahead and break up the parentheses with the distributive property. We'll call that xy minus 3x equals 2. Again, my eyes are on the y. That's what I'm trying to isolate. So let's add 3x to both sides. And then we'll go ahead and divide both sides by x. And I'm going to divide the entire right side by x. So we come up with the equation y equals 2 plus 3x over x. In function notation, and let's rewrite that numerator in descending order, we could call this 3x plus 2 over x. So we could certainly graph both of those to visually verify how they're inverse functions, but I want to talk about something else. The original function was a rational function. Notice it has a vertical asymptote where the denominator is equal to 0, that is at x equals 3. And because the degree of the bottom is bigger than the degree of the top, that's, remember, the Bobo case, it has a horizontal asymptote at y equals 0. Now take a look at the inverse function. Notice the inverse function has a 0 in the denominator, so the equation of its vertical asymptote would be x equals 0. And because the degree of the top is equal to the degree of the bottom, we have a horizontal asymptote at the ratio of leading coefficients, which would be y equals 3. So compare the asymptotes of the original function to those of the new function. Notice from the original function f of x, we had a vertical asymptote at x equals 3, but on the inverse function, it became horizontal at y equals 3. In addition, if we look at the original function, there's a horizontal asymptote at y equals 0, but it became a vertical asymptote at x equals 0. So everything is switching and reversing when we generate that inverse function. In the next video, we'll look at an algebraic way to verify if two functions are inverses.